We are going to analyze here the matrix representation of the fully implicit method for the diffusion equation. Okay, we already got the finite difference representation for the fully implicit method, which is this one. And these are represents like n minus 1 different equations that have to be applied at all the j times. So n here, the n here, raising here, it will go from 1 to nx minus 1, where this nx represents the number of space steps you are considering the x variable. And the alpha parameter here, as usual, is d times delta t over delta x squared. So we are going to see that equations here, so all these nx minus 1 equations can be all at once represented by these matrix representations. So here on the left, we have like nx minus 1 different u values, and this all are represented here in this column form, where the number of rows here is nx minus 1. Then on the other hand, the values of the u function that are entering these equations are, however, nx plus 1, because we have here that n minus 1, and you have here n plus 1, and these are represented in this other column here. These are the ones that are evaluated, as you can see here, at j plus 1, while the ones on the left are evaluated at j. So the number of rows here are nx plus 1. And these are connected by this intermediate matrix, which is the connection between the two sides, which are the coefficients that we do have here. It's pretty simple to see that this matrix representation actually corresponds to this finite difference representation we do have here. Okay, for example, let's apply it for the n value equal 1. If you apply that, we have the n1 evaluated at time j, which is this one here. Okay, it corresponds to the multiplication of this row here with this column here. So it corresponds to the minus alpha times u0 evaluated at time j plus 1, which corresponds to the product of minus alpha times u0 plus 1 plus 2 alpha u1, which is the multiplication of this one with this one, minus alpha times u2, which is the multiplication of this one times this one. And there is no others because you have all the rest of the elements in this row are 0. So you can check with the others and see that this is actually the matrix representation. And as you can imagine, our aim will be to get the expression for the u function evaluated at time j plus 1 as a function of the u values evaluated at the previous time step at time j. So for that, what we'll need to do is we'll need to bring that matrix here to the other side of the equation. Actually, for that, what we have to do is you have to use the inversion of the matrix. But for that, we need the matrix to be a square. And it's not a square because you can see here the dimensions of the matrix are nx minus 1 and nx plus 1. So you cannot do the inversion. So you have to use some strategy in order to make that matrix a square. And that's what we are going to do next, actually. So, as we have said, the matrix has, actually, this should be, the matrix has nx minus 1 rows and nx plus 1 columns, which is a representation of the nx minus 1 equations that we have seen in the finite difference representation for the fully implicit method. But we do have nx minus plus 1 unknowns, okay? Because we have to take the u value at different, at nx plus 1 different space points, if we are considering that the number of space steps are nx. So the two equations that we are missing actually here are coming from the boundary conditions. And using these boundary conditions, we are going to convert this system of equations into a system of equations involving a square matrix. So the strategy is going to be to use these boundary conditions in order to convert the previous matrix we have seen before, this matrix here, in a square matrix. Okay, so again, the aim that what we need to do is we need to transform these matrix representations we have just seen in order to have the following. So actually we have done actually is we are going to bring to the left actually everything which depends on j plus 1. And we're going to put on the right everything which depends on j. So our aim is going to be the following. Use the boundary conditions in order to write this hand side of the equation, which is the left hand side of the equation, which depends actually on j plus 1. We're going to write it in this way. Some matrix, which is going to be calculated at time j plus 1, and as going to be in the left hand side of the equation, we are going to label that with L, which corresponds to the left hand side, times some u vector, which is calculated at time j plus 1, plus some vector actually evaluated at time j plus 1. It's equal the u vector, which is this one, evaluated at j. So the idea will be transform this matrix representation, the following one, where this M is going to be a square matrix, plus then we are going to have another column, and this column is going to have information on the boundary conditions. So it's going to incorporate information on the boundary conditions. How we are going to do that? That's what we are going to do next. And for that, of course, it's going to depend on the boundary conditions. We are going to analyze two different cases. Once we have the Dirichlet boundary conditions, on the case that we do have like Neumann boundary conditions.